For this video, we are going to use the definition for the limit of the complex function to show that the limit of your z squared as z approaches to 2 is equal to 4. This is the second video on showing the limit of a certain complex function to be true using a given definition. Okay, so we had the previous video, we had the linear function for your complex function. This time, we have a quadratic complex function, and we also have another one later on. Now, take note that for this instance, we just need to use the definition, but for that, we know here that our function of f of z is actually z squared. Okay, our z sub 0, okay, is actually your 2, or that's the value your z is approaching to, and your 4, that's your limit. Okay, that's the limit for your 4, because we just need to do that because we need to show that this is true. The limit of your f of z as z approaches z sub 0 is equal to L, using a definition that if for every epsilon greater than 0, okay, there exists delta greater than 0. That's our goal, to find the value of delta, such that whenever, or you can say here, if your z minus z sub 0 is greater than 0 but you're less than your delta, then your absolute value of f of z minus L is less than your epsilon. This is the definition, not necessarily complete, but the portion of the definition which we need to show. That would mean we need to find a value or representation for your delta that must be greater than 0 for every epsilon greater than 0 that would satisfy this using this perspective as well. So we know that our z sub 0 is 2, okay? So that would mean this portion here, we will approach a certain expression of z minus 2 must be less than your delta, okay? And at the same time, this goal here, okay? Now, for this to be true, there are some references which would actually target this, attack this in a direct proof. But for the purpose of reviewing as well some processes we had in the previous video, and for the proof of real analysis in other playlist for this channel, let's do some scratch work. The purpose of the scratch work is that we would be guided at our direction. At the same time, we would have already an idea on what would be our delta that we need to use in our proof. Because if you're going to use direct proof for this without using scratch work, and if you can still find a certain representation of delta, and that's good. But for some instances, some functions is difficult to predict. That's why we need to do this scratch work. And this is my scratch work here, so pardon. Our goal is this, okay? So we need to show a certain direction for our delta. We need to show that our absolute value of f of z minus L must be less than epsilon. And our goal is to find, again, a certain delta. We have our value for f of z here and our L. So let's just simply plug them in. You have your, sorry, that's z squared minus your 4 must be less than epsilon. Let's go away with epsilon first, because our goal is to find out as a representation of delta. And take note, we have this form here. Our delta is greater than, or greater than this expression. So we just need to show this form, or have this form in z minus 2. We know that it's the difference of two squares. Again, let me go away with delta first. It's actually z plus 4, and then you have your z minus 4, right? So the, sorry, not 4, my bad. Z plus 2 and z minus 2, okay? So z plus 2 and z minus 2. Notice that z minus 2 is already here, and we know that to be less than delta, so it's already there as a representation. However, z plus 2 is not needed for the not necessarily not needed, but not available as a representation for our delta. So what we can do here is, of course, separate them by the property of the product of absolute value. Again, sorry, my bad. This is actually 2, right? Z plus 2 and then z minus 2. Again, this should be less than epsilon. And since z minus 2, or the absolute value of z minus, is less than delta, so we're halfway there. What we need to do here is to come up with the representation for this. So allow me to have some assumptions first for our delta. Okay? So since we have here this representation, okay, so it's very obvious. I'm gonna insert some concept here. Okay, if delta is equal to 1, so with this form, this one here, that would mean your absolute value of z minus 2 being less than delta, which is equal to 1. So we have here the absolute value of z minus 2 is less than 1. What's the purpose of this? The purpose of that is later on, we can we need to manipulate that and identify a certain z plus 2 expression. So what we could do here is this. We know already the properties of absolute value. So we'll have here negative 1, z minus 2, and you have here 1. We want this to be plus 2. So what we would like here is to add 6 here. Sorry, not add 6, add 4. Sorry, add 4 here and add 4 here. So you will have here 3 less than z plus 2 and less than 5. Okay, what's the purpose of this? Z plus 2 is here. So that would mean if we are going to take the absolute value of z plus 2, it's also less than 5 here. Because this is just the absolute value of whatever that value of that z, it will always be less than 5. And if we're going to have the absolute value of that, it's also less than 5. Okay, so if it's less than 5, we can now plug that in here to get another representation for z minus 2. The first representation for z minus 2 is this one here. Once we assume our delta less than 1, we just want z minus 2 because that is the item we would like here to show for us to show this equivalence. Okay, so that would mean plugging that in our resulting earlier, we have the absolute value of z plus 2 and the absolute value of z minus 2 is less than your epsilon. This is actually equal less than 5, so 5 times the absolute value of z minus 2 less than epsilon. So we have here the absolute value of z minus 2 could be represented by epsilon over 5 as well. Okay, and this again less than delta. So we have two representations for delta equal to 1 and this one here, epsilon over 5. So what we have here is our delta could be the minimum. Okay, it could only take one value of your 1 and epsilon over 5. If you use 1, then it satisfies the value of your epsilon over 5. So with that, we're just going to use here epsilon over 5 because it's the resulting value once we applied our value for delta, which is equal to 1. So we have here now our existence of our delta. Let's now have our proof. Yes, this is the time that we have our proof after our scratch work. Again, we're doing the scratch work to make sure that we can represent our delta well. But again, if you can attack this in just one direct proof, why not? I'm just using this because this is more comprehensive for us to, and in studying this proof. So we have here assume. Okay, we're going to assume our delta be the minimum of your 1 and epsilon over 5. Okay, so we're going to have, since the delta is not existing, okay, this one here, for every epsilon greater than 0, we have that first statement. And since there exists delta and then we have shown the delta, then we can now invoke here this statement. Then if 0, z minus z sub 0 is less than delta, or in this case, you will have 0, z minus 0, z sub 0 is 2, is less than your delta, and your delta could take two of these values, okay, any of those two values. So we can now have f of z minus L and show that it's less than epsilon. Okay, that's the definition. Since we're using epsilon, then we will be using this second value, but we will have to do it step by step. Your f of z is z squared. Your L is 4. The purpose of the scratch work is for us to be guided the same process doing backwards. So you have here z plus 2, z minus 2, which is equivalent to the separate absolute value notations. Okay, and since we had the scratch work earlier, okay, that's the reason why we had the scratch work. We have this item here. Okay, so the z plus 2 is less than 5 when we assume that delta is equal to 1, and that's possible here because our delta could be the minimum of 1 and epsilon over 5. That would mean we can now invoke here that says this value is less than 5, so basically you have less than 5 and times your z minus this one here, which is actually less than delta, and your delta could take another value of epsilon over 5. So you have here epsilon over 5. Okay, that would mean that we can cancel that, and you will have here less than epsilon. So with all of this, cutting the middleman, you have here until here. Hence, the absolute value of f of z minus L is less than epsilon. By the way, again, the reason for this is this notation here, and that is why we had our scratch work earlier. So we have shown already our target for our definition. Then we can now say here, since epsilon greater than 0 is arbitrary, then we can conclude that since we have arrived here, the limit is true. The limit of z squared as z approaches 2 is equal to 4. This is the proof for the second item. Again, the scratch work is very important. Some of our references and professors will have different styles, but generally once you will have your scratch work, it will guide you and help you in showing the proof using the definition. Thank you very much for watching.